As per American Concrete Institute ACI 211.1, methods for selecting and adjusting proportions for normal weight concrete both with and without pozzolanic material is based on two methods. One method is based on an estimated weight of the concrete per unit volume. The other is based on calculations of the absolute volume occupied by the concrete ingredients. The absolute volume method of mixed design, as described by the ACI method, is briefly presented in this session with design steps for mixed proportioning of M20 grade concrete. ACI mixed proportioning method is suitable for normal and heavyweight concrete having maximum 28 days cylinder compressive strength of 45 megapascal or 45 Newton per mm square. For concrete proportions to be acceptable, the average compressive strength of concrete from trial batch test must be equal or exceed the target mean compressive strength. The standard deviation established from test records is a measure of the concrete supplier's ability to manage the variability of materials, production and testing of concrete. When a concrete production facility has a suitable record of 30 consecutive tests of similar materials and conditions expected, the sample standard deviation is calculated from these results. This sample standard deviation is used to determine the target strength as per table 5.3.2.1, page number 69 of ACI 318.11. So this formula is given like for target strength less than equal to 34.5 megapascal. Formula is given as maximum of the specified compressive strength plus 1.34 times standard deviation, or specified compressive strength plus 2.33 times standard deviation minus 3.45. For target strength to be greater than 34.5 megapascal, target strength is given as maximum of two formulas. One is specified characteristic strength plus 1.34 times standard deviation, or 0.9 times specified compressive strength plus 2.3. So this formula is applicable when we have standard deviation result established based on minimum 30 number of test results. Suppose if we have test results less than 30 but at least 15 are available, the calculated standard deviation is increased by the factor given in table 5.3.1.2, which is presented page number 68 of ACI code 318.11. When field data to establish a standard deviation are not available, the target mean strength can be obtained from table number 5.3.2.2, page number 70 of ACI code 318.1. Here that table has been presented with the SI unit. There you will be finding the units in pound per square inch. So here the units has been given in megapound. Like if the specified compressive strength is less than 21, then the formula for target mean compressive strength is specified strength plus 7. If the specified compressive strength lies from 21 to 35, then target strength becomes specified compressive strength plus 8.5. If strength is above 35, then the target mean compressive strength becomes specified compressive strength plus 10. Now in our example of mixed design, the grade of concrete being considered is M20. So specified compressive strength is 20 megapascal. So therefore, as per the ACI 318.11 provision, the concrete mix will be designed for target mean compressive strength of how much? It will be designed for F-C plus 7, that is 20 plus 7. So it will be 27 megapascal. In the previous video of proportioning and general steps for mixed design, step 1 was about required material information. The information which needs to be collected is on the maximum nominal size of coarse aggregate, grading of fine and coarse aggregate, with information on fineness modulus of fine aggregate. This information can be determined by conducting a sieve analysis. Next, determine the unit weight, specific gravities, and absorption capacity of both the coarse and fine aggregate. Also, determine specific gravity and type of cement to be used for making the mixed design concrete. For our mixed design problem, by conducting required experiments on materials, the following information is collected. Crushed coarse aggregate is angular in shape and have nominal maximum size of 19 mm with specific gravity of 2.8 with dry roded mass of 1600 kg per meter cube. The moisture content which is found in crushed coarse aggregate is 1% with absorption of 0.5%. Now, in case of fine aggregate, it has been determined that its fineness modulus is 2.8, the specific gravity is 2.62 with moisture content as 4% and absorption of 1%. Portland slag cement with specific gravity 3.15 is being used to make the concrete. Step 2 is about choice of workability. Based on job requirement, select the workability. If the workability in terms of slump is not specified for a particular job, select an appropriate value from table A 1.5.3.1, which is there in page number 21 of ACI code 211. Here, suggested range of workability is available in terms of slump given in millimeter. The slump value has to be increased by 25 mm if compaction is done by hand or rodding, etc. For our example, let us adopt workability of 75 to 100 mm. In step 3, which is estimation of mixing water and air content, we consider workability as well as the maximum size of aggregate, and with these two reference, the quantity of mixing water and approximate air content per unit volume of concrete may be determined from page number 22, table A 1.5.3.3 of ACI code 211.1. It must be noted that the water content provided, as can be seen in this table, table A 1.5.3.3, whatever water content has been mentioned, it has been for non-air entrained concrete as well as air entrained concrete. For the given slump, as you can see here, we have the slump values, and in this direction we have the maximum size of the coarse aggregate. So with reference to slump and the maximum size of the aggregate, the water content has been defined. Now it must be noted that the water content provided here is for angular shaped aggregates. In case aggregates are round, the recommended trial water content will be reduced by 18 kg for non-air entrained concrete, and it should be reduced by 15 kg for air entrained concrete. For our design mixed concrete, which is a non-air entrained concrete, the nominal maximum size of aggregate is 19 mm with workability in the range of 75 to 100 mm slump. So our water content per meter cube of concrete will be 205 kg. So the trial water to be added on the concrete can be 205 kg. Also, we can estimate the approximate amount of entrapped air which is going to be present in the mixed design concrete. It can be considered as 2%. So the water content requirement is 205 kg per meter cube with approximate air content as 2%. Step 4 is to determine the water cement ratio. In general, a lower water cement ratio produces stronger and more durable concrete. If natural pozzolanas are used in the mix, then the ratio becomes a water cementing material ratio, with cementing material being Portland cement plus pozzolanic material. The water cement ratio is selected from table A 1.5.3.4a, which is in page number 22 of ACI code 211. We can obtain the water cement ratio also from figure 3.1 of ACI code 211.3 in page number 5. In our case, the target compressive strength is F dash CR is 27 mega. 27 megapascal is going to lie between 25 and 30. So we need to do the interpolation in order to determine what would be the water cement ratio. Since we have non-air entrant concrete in our example, if we interpolate, we get the adopted water cement ratio as 0.582. We have to do the interpolation between 0.61 and 0.54 because our target compressive strength for mixed design concrete lies between 25 and 30. If we do the interpolation, linear interpolation, we get the water cement ratio as 0.582. Next is to calculation of cement content. We can calculate cement content from the water content and water cement ratio as determined in step 3 and 4 for the required strength and durability. We had determined the water content as 205 kg. We have water cement ratio determined as 0.582. So we get cement content as 352.23 kg. Let us adopt cement equal to 354. So we are going to adopt cement as 354 kg in our mixed design. Step 6. Estimation of coarse or fine aggregate content. The coarse aggregate content is estimated from table A 1.5.3.6, which is given in page 23 of ACI code 211.1. With reference to the nominal maximum size of aggregate, which is given over here, and fineness modulus of fine aggregate, we can compute the volume of dry rodded coarse aggregate per unit volume of concrete. Points to be noted when we use this volume of dry coarse aggregate per unit volume is that this value has been determined for aggregate with specific gravity of 2.68. For any aggregate having specific gravity other than 2.68, this value should be multiplied by the ratio of 2.68 divided by the specific gravity of the given aggregate. Moreover, for less workable concrete, such as required for concrete pavement, this value may be increased by about 10%. If workable concrete is needed, such as when placement is to be done by pumping, this value can be reduced by 10%. For the mixed design problem, of M20 grade concrete, we have maximum size of aggregate as 19 mm with fineness modulus of fine aggregate as 2.2. Referring this to value, we get the volume of dry rodded coarse aggregate per unit volume of concrete as 0.62. If we remember, the specific gravity of coarse aggregate was 2.8, which is other than 2.68. So this 0.62 value has to be multiplied with 2.68 divided by 2.8. So let us compute the volume fraction of coarse aggregate, which is 0.62 corresponding to 19 mm maximum size of the aggregate and fineness modulus 2.8. Since specific gravity of the coarse aggregate is 2.8, which is other than 2.68, this value 0.62 has to be multiplied with the ratio of 2.8 0.68 divided by the specific gravity of the course. This comes out to be 0.593. Now, the mass of coarse aggregate can be multiplied with the volume of dry rodded coarse aggregate with the density of dry rodded coarse aggregate, which has been determined in the step 1. So we get mass of coarse aggregate as 0.593 into 1600, which is equal to 949.5 kg. Let us adopt mass of coarse aggregate. Adopt mass of coarse aggregate as 950. So we are going to adopt 950 kg as the mass of coarse aggregate in our trial mix proportion. Now we'll be computing the mass of dry fine aggregate. We have computed mass of cement, water and coarse aggregate for 1 meter cube of concrete. So the volume of concrete considered is 1 meter cube. Now we would like to know how much amount of volume is being occupied by cement, water, entrapped air and coarse aggregate, so that we can compute the volume of dry fine aggregate. So what will be the volume of cement? Volume of cement is mass of cement by density of cement. We have adopted 354 kg for 1 meter cube of our design mix concrete. The density of cement is specific gravity of cement into 1000. This gives the volume of cement as 0.112. What is the volume of water? Volume of water will be mass of water by density of water. Mass of water, which we have adopted, is 205 kg. Density of water is 1000 kg per meter cube. So this gives the volume of water as 0.205 meter cube. Volume of entrapped air, this we have computed corresponding to nominal maximum size of aggregate as 19 mm, which came as 2% of 1 meter cube of concrete. So the volume of entrapped air is 0.02. So what will be the volume of dry coarse aggregate? The volume of dry coarse aggregate will be mass of coarse aggregate by density of coarse aggregate. So what is the mass of coarse aggregate? We have adopted 950 kg as the mass of coarse aggregate. Density of coarse aggregate will be specific gravity of coarse aggregate into 1000. So this gives the volume of dry coarse aggregate as 0.34. Now, in order to compute the volume of dry fine aggregate, this can be computed by deducting the total volume of concrete with volume of cement, volume of water, volume of entrapped air and volume of coarse aggregate. If we do that, we get 0.32. So what will be the mass of dry fine aggregate? It will be volume of dry fine aggregate into density of fine aggregate. Density of fine aggregate is specific gravity of fine aggregate into 1000. So this gives the mass of fine aggregate as 846.26 kg. Let us adopt the mass of fine aggregate as 845 kg. Since this is a trial mix, we can adopt the value close to computed value. So we are adopting 845 kg as the mass of dry fine aggregate. Now we can compute the proportion based on dry aggregate condition. How much cement we have? We are using 354 kg of cement per meter cube of trial mix concrete. Fine aggregate, we are adopting 845 kg of fine aggregate, whereas the coarse aggregate which we are adopting is 950 kg. If we divide this proportion by 354, we get 1:2.4, 2.7. Step number 7, adjustment for moisture in the aggregate. For the design mix problem, we have total moisture of 1% in the coarse aggregate and 4% in the fine aggregate. If the trial batch proportion based on assumed concrete mass are used, the adjusted aggregate masses becomes, so in case of coarse aggregate, if we are taking the site condition and making the trial batch concrete, then we have to consider the weight of the moisture that is going to be present in the coarse aggregate along with the dry aggregate. The dry aggregate weight which we have is 950 kg. Now this has to be multiplied with 1.01 so that we get the mass of aggregate which are in wet condition. So this comes out to be 959.5 kg. Now the mass of wet fine aggregate, the mass of dry fine aggregate was adopted is 845 kg. If the fine aggregate is wet, it means there is the mass of water also, so that has to be added in the fine aggregate which we are going to use to make the batch concrete. So 845 into 1.04, so this gives me 878.8 kg. So when we are making a trial batch concrete based upon the supplied aggregate, we have to use coarse aggregate as 959.5 kg and fine aggregate as 878.8 kg. Now we have to adjust the water that need to be added to make concrete, because we have the moisture already present in coarse aggregate as well as fine aggregate. Absorbed water does not become part of the mixing water, so it must be excluded from the adjustment in added water. In case of fine aggregate, the water absorption was 1%, whereas for coarse aggregate the water absorption was 0.5%. So the net water or the net surface water which is going to be present in fine aggregate will be the surface moisture present in fine aggregate minus water absorption in fine aggregate. So this is the free water which is going to be present in the water, 4.1%. So this much percentage of free water is going to be present in fine aggregate. Now this has to be multiplied with how much is the weight of the fine aggregate. So the weight of fine aggregate which we are considering is 878.8 kg. So the free water comes out to be 26.4 kg. Similarly for coarse aggregate, the free water which is going to be present is, what is the surface water, 1% minus water absorption divided by 100. So this much percentage is there as the free water. This has to be multiplied with the mass of the coarse aggregate which is 959.5. So the free water in coarse aggregate will be 4.8 kg. So the total free water in aggregate will be 26.4 plus 4.8, 31.2. Hence, amount of water to be added at the batching plant, we have to deduct this free water from the trial adopted water that need to be added in our concrete. So the water which we adopted was for dry aggregate, whereas the aggregate will be in moist condition at the site. So we have to consider this into account when we make concrete, because these aggregates are going to supplement water in the concrete. So whatever water is being supplemented, that has to be deducted from the water which had been adopted based on dry aggregate condition. So 205 minus 31.2, this comes out to be 173.8 kg. 173.8